Okay, today I'm going to talk about polar equations and calculus. This is going to be part one. So specifically in this video, we're going to talk about dy over dx, or the slope of the curve. In polar equations, we get stuff that looks like this. It sort of spirals around a pole. But dy over dx is still the slope of the tangent line to that curve. So dy over dx, we're going to treat this similar to the way we treat parametric equations, in that we're going to call this dy over d theta over dx over d theta. So when you're given a polar equation, so we would get something like r of theta, right? So we get an r output in terms of theta. So r equals, and then stuff happening with theta. The first thing we want to do is we want to write that essentially as a parametric equation. So a parametric equation, x equals in terms of theta, y equals in terms of theta. So we can always easily go back and forth between parametrics and polar, because from when we did the whole going from rectangular to polar or vice versa, keep in mind we had x is equal to r cosine of theta. So this will be the function r of theta, cosine theta, and then y is going to be equals r of theta, and then sine of theta. And if you forget where that comes from, if we look at sort of a polar graph here, we have theta, we have r, we have x, we have y, and that's just SOHCAHTOA. So sine is y over r, so we can solve for y, and the same thing for x, but in terms of cosine. Okay, so when I take the derivative of this, and this ends up always giving us a formula. I've had students that memorize this formula. Personally, to me, I like to keep the memorization to a minimum, so we keep in mind that x equals r cosine theta, y equals r sine of theta. And then when we take the derivative of this, we take the derivative of this on top. So let's take the derivative of the r part first. Copy down the sine, and then plus copy the r of theta down. And the derivative of sine is cosine theta. All right, and then we get r prime of theta. So we're taking the derivative of the x part now. Copy the cosine down, and then copy the r down. Derivative of cosine is negative sine, so we'll make this a minus. So we can always do this as a formula. Personally, I like to do it depending on the problem, which I'll show you here in a moment. Okay, so let's take a look at an example. Okay, so here's our problem. We're given that polar function, right? Theta is the input, the output would be our r, how far we are from the pole. We want to find dy over dx when theta equals pi. So the first thing I'm going to do here is I want to turn this into a parametric equation. So I'm going to get x is equal to r, so that will be 2 plus 3 sine of theta, and then that's cosine, right? So r cosine theta, so we just write this as a function. And y will be 2 plus 3 sine of theta, the r, and then sine of theta. Okay, so now to get dy over dx, I just simply take the derivative of this. So this is the way I keep in mind. I don't memorize this as a formula as I showed you before. I just take the derivative of this. So I treat this as two separate parts. Let's take the derivative of that first. So that's going to give us 3 cosine theta. Copy down the sine. Okay, now we got to do product rule, so this will be plus, copy down the r, 2 plus 3 sine of theta, and take the derivative of sine, that's cosine theta. Okay? Keep that memorization to a minimum. We all know how to do product rule, so if you remember just to write x and y as a parametric equation, I think that's the best way to do it. All right, so now let's take the derivative of the denominator. Once again, the derivative of 2 plus 3 sine of theta is 3 cosine of theta. Copy down the cosine theta. If you want to call that cosine squared, be my guest. You don't have to, though. And now we take the derivative of the cosine. So this will copy down the 2 plus 3 sine of theta. Derivative of cosine is negative sine, so I'll make that minus. Okay, so this is our dy over dx in terms of theta. Okay, so we want to know what dy over dx is when theta equals pi. Okay, so I'm going to plug, everywhere I see a theta, I'll plug in pi. Now the good news here is any of these sine of thetas will just zero out. So this whole term will zero out, plus this term will zero out right here, so that leaves us with 2 plus 0. And then cosine of theta, think unit circle, is negative 1. Okay, now here we have 3, and this is going to be negative 1 squared. I'm just writing it so we can see that, right? So negative 1 times negative 1, that's going to end up being positive 1. Minus, and then once again, sine of pi gives us 0. So then we equals negative 2, and then that's 3. And that is the slope of our equation when theta equals pi. So if we graph this and looked at when theta equals pi, we would get a tangent line that's roughly negative 2 over 3. So that's the slope of our equation. Now, if they want us to write the actual equation, and I'm not going to do this because a lot of this is going to mirror what we do with parametrics. So if we wanted to write the tangent line equation, we'd have our slope. Realize to get x, I'm going to plug this theta in here, right? So, well, let's do that. Even though I didn't ask for it at some point, you're going to do that. So x is equal to, plug pi in. So this is going to be 2 plus negative 1, so that's negative 2. And then y of pi is equal to 0. So my tangent line would be y minus 0 is equal to negative 2/3, and then x plus 2. You can distribute that if you want, or just leave it like that. So that'd be the tangent line. Okay. So once we change this to a parametric situation, it's very similar to what we were doing with parametrics. Also with that, you could be asked a question, for instance, where is the tangent, when is the tangent line horizontal? Excuse me. So horizontal, of course, would be when dy over dx equals 0. So that would mean the numerators equal 0. In other words, when dy over d theta is equal 0, or they could ask a question, when is our tangent line vertical, which would be dy over dx doesn't exist, which means the denominators equal 0. And like I said, I'm not going to go through those problems are pretty involved. Take a look at the video we did with parametrics if you need a refresher on that. Okay, so that's it for part 1. In part 2, I'm going to talk about area enclosed by a polar equation.